So Jay was a PhD student in my group and did a lot of really interesting work on the low temperature optical properties, a lot of these two-dimensional materials. And when we're talking about robotic mechanisms for creating heterostructures, this is one. So he's exceptionally talented at finding monolayers, stacking kind of absurd numbers of monolayers, and making amazing devices. Since then, he's moved on to better pastures, and he's at Qrypt, where he's their one and only quantum physicist. Right?
Yep.
Yeah. They haven't hired another one yet, right?
No, not yet.
Not yet. They learned their lesson the first time. So Jay is going to talk about what he does there. So I'll leave it to him.
Thanks, Patrick. Good afternoon, everyone. So feels really odd to give a talk here today for some reason to graduate students, to professors I work with, coming back to Mason after a while. And it's not the kind of talk that I particularly give, which is very physicsy in nature. This one doesn't even have a single plot in it. So it feels so weird and different from an APS March meeting talk. But it's just sort of a disclaimer for what's to come, because I can pretty much tell you that I'm not really an expert on crypto as of yet. I mean, it's only been a year for me to make that transition from condensed matter systems and probing material science like probing low dimensional materials to jump to quantum cryptography. Yeah, let's get into it. So the company so the company I work at, which is Qrypt, is a startup in the quantum information security and quantum cryptography space. It's founded by two ex-CIA employees. We are located in New York on the 83rd floor of One World Trade Center, so amazing views. And one of our offices is located in Maryland here, where all of the cool hardware design, development, testing, and everything, cool engineering goes on in Maryland. And most of the software development side and cryptography side is up in New York. It's an American owned and operated company, vertically integrated. And one of our missions at Qrypt, or well, a broader mission at Qrypt, is to develop technologies that eliminate the security threat of post-quantum era. So the era that we are talking about is an era where quantum computers are scalable, they are easily available, feasible, and what that would do to our current encryption systems, our current, as Joseph was talking about in his talk, like all of our current RSA systems or our antisymmetric key systems and cryptography systems would become obsolete. So we are focused on developing technologies that can secure our data or our privacy in that particular era. And that problem is actually a twofold problem. So the first challenge to that problem is securing your data through some sort of an encryption key that is not only quantum resilient, but quantum safe. So what you do is you develop some sort of, that's what we do. We develop some sort of a hardware device based around some patented technology from a bunch of physicists in several national labs, develop a hardware platform that can perform onboard quantum measurement, generate some sort of an entropy from that, convert that entropy to quantum numbers, convert those numbers to keys, and then your keys are quantum safe because they come from some sort of a quantum measurement rather than some algorithm that's classically written or mathematically written. So that's first part of the challenge, and that's what we typically do. We form these collaborations with national labs. And the second part of the problem is once you have that data encrypted, you still need to send it from one point to the other point, providing end-to-end encryption. And typically, what people mostly do is, you send your data that is encrypted, but that goes along with the key you use to encrypt that actual data, which is again a risk. So that second part of the problem that provides, because even if your quantum numbers are good and come directly from some sort of a quantum process, if you send keys generated through that process in your data path through some sort of a classical channel, then you're not really doing anything different than what is typically done today. So the way to get around, Qrypt's way to get around that problem is that they have developed this infrastructure that can generate encryption keys at multiple endpoints. So point A and point B, it can generate keys at those endpoints without actually distributing through them with using some sort of a classical network. And that work has been done by this is a pioneering work, and it's been done by our chief cryptographer, Yevgeny Dodis, who is a NYU professor and ICR fellow. And that work is published, it's patented, so anyone can look it up, see the math, see the assumptions, see what the goals are, and make sense of it on your own. So that's something that also sets us apart. Like lots of companies in this space don't really want to share their information or share their technologies or share their ideas around, but most of our work, almost all of our work, is either patented or it's published in some sort of a peer-reviewed journal. So that's the second part of the challenge. So Qrypt overall, I would say that what Qrypt is trying to do is basically build a sort of a security as service platform. So, and when I say security as service, what I mean is that we have an ability to basically integrate into any existing architecture, any existing workflow to secure your data, like and secure the communication channel. And that's not just in paper. Like so, this year we actually reached a great milestone for both of those challenges. So we deployed a US designed and manufactured quantum random number generator this year in Feb. So this performs some sort of quantum measurement on a piece of hardware, on a piece of PCB, extracts some sort of entropy from it, converts that to random numbers, and converts that to keys. And then the second one is this collaboration with Megaport. Megaport is a company that does that provides network, I think, communication across like multiple, like hundreds of different public clouds and data structures. So you have a platform that connects several hundreds of data clouds and public data centers together, and then you have a mechanism where you can encrypt and secure all of that traffic. So it's basically like aim your traffic through a tunnel that's been developed by Qrypt, and we can promise that it comes out secure at the other end. And not only that, like as I was saying, like for developing all the hardware tech, we collaborate with Los Alamos, Oak Ridge, and EPFL. EPFL is one of the premier research institutes in Switzerland. We have industry academia partnerships with QEDC and NSF and Mid-Atlantic Quantum Alliance. And then we have a whole bunch of actual applications, so actual products that come out in the market, where we have built partnerships with companies like Voltri, HashiCorp, Megaport, Kerasoft, to actually secure data through the quantum key generation technology that Qrypt has developed. So what does the landscape look like at least in the information sector? This talk was supposed to be a bit about Qrypt and a bit about what actually is offered in this space. And so, like US government, beginning with the National Quantum Initiative, and then through a flurry of different executive orders, memorandums, and directives, all either a part of the QCCPA Act, which is the Quantum Computing Cybersecurity Preparedness Act, or something else, has proposed a need to sort of follow some sort of a post-quantum cryptography standardization across all US agencies and its partners. So this will basically trickle down to all businesses, both in the private and public sector, and not only in the information sector, but like all sectors that require some sort of data authentication or some sort of secure data transmission or storage. And this will, again, this will open up avenues and career paths that require you to apply some sort of a quantum mechanical principle to an existing technology, which is what entirely Qrypt does. Like we don't really, we develop a solution and we integrate that to any of these other networking companies or data transmission companies, and that's where we are at. So what I and my work, so it's been a journey for me actually. I did experimental condensed matter here. I started as a master student from a electrical engineering background, and then moved to Dr. Bora's lab and did research for, I guess, 5 years or 5.5 years. And then right about the time that I was about to graduate, I guess around September, I was graduating in December, I started interning at Qrypt and in September, around September. So that gave me a 3-month window, both for me and for Qrypt to sort of understand, because Qrypt is essentially a hardware company, and most of their work is hardware and software side. It's not really a physics company or a condensed matter company or a material science company or something like that. So it was tough to see right on, like at least in September, as to how that fit is going to be like. Because essentially all my role is talking to a bunch of engineers all the time, or working with hardware engineers, FPGA engineers, cryptographers, software engineers, to try and develop these systems that can run quantum measurements on board and then evaluate the results of those measurements. So it's like they don't have any background on quantum mechanics, and I don't have any background on hardware schematics or FPGA. So it's sort of a really collaborative effort, but it's like I did have to spend about 6-7 months trying to learn the language, trying to learn how to look at hardware schematics, trying to look how a very log code looks like, and things like that. And since all of our hardware platform and technologies that surround it are developed from some sort of a patent licensed by either like ORNL, like Oak Ridge National Lab, or Los Alamos National Lab, or EPFL, you get to work with a ton of physicists from those teams as well. So that's where most of my work is. Like, I still get to talk to a whole bunch of engineers, but most of my collaboration is with the team of physicists that help us develop these techs in-house. And so based around that, I mean, Joseph actually did a good job at covering what the industry has to offer, at least in the quantum space. And the 4 points that I have listed here are the 4 applications for quantum technology: quantum sensing, quantum communication, quantum cryptography, and quantum computing. So this is pretty standard. I think it's pretty well known. I think I graduated around in 2021, and when I was looking for jobs, there were about 60 or 70 companies back then that were just in the realm of like starting up, or were startups looking for physicists, looking for engineers with physics background and things like that. So QEDC has a ton of ton of other companies. Like this is one of the plots that I found from one of these studies done back in 2020, which pretty much interviewed all the partners within the QADC consortium, and sort of graphed up a degree versus the number of people, or the percentage of companies reporting. And as you can see, I mean, PhD physics is pretty much bang on there. And as Joseph was saying, like, it's not just PhD. I mean, you have a 38% companies would also need bachelors in physics and masters in physics. So it's not only limited to PhDs, but I mean, having PhD is for sure a strength. And again, it's all about like building your own network. Like, I got through to Qrypt via a relationship that Patrick had. It was still not like, it was still very much in the realm of, okay, let's see if things work out. If it doesn't work out, we'll part ways. But those 3 months were crucial because we had built some sort of a relationship with them, and like having some sort of an interdisciplinary approach. Because again, like, if you want to work in a company like this, you've got to work with hardware engineers, electrical engineers, FPGA engineers. So if you have some sort of an engineering background, even an ability to solder things on, great. Like, that's the sort of stuff that will always help you and stand you out. And yeah, that's the last page there with a shameless plug of Qrypt and the amount of opportunities we have. So we are hiring all sorts of engineers. We are hiring people with physics background, especially who have a degree in engineering, who have a computer science degree, or who have a electrical engineering degree, or a hardware engineering degree with some sort of a background in physics, and then cryptography as well. So check us out. And with that, I'll leave you with this mysterious thank you page that my company had me put in. But that is not me. I would have loved to be that guy. Don't know what he's looking at though.
That's the future.
But yeah, thank you.
Questions for Jaydeep? Echoing is acceptable. Jeff, are you allowed to share the hardware version?
Yeah, so I don't have it right now, but so we have 3 projects right now, and all of those projects derive their quantum entropy from some sort of quantum noise signal that has its base in quantum mechanics. And all of those 3 projects have patented technology, patented by those national labs, which are up for grabs on Google. So anyone can look those up, see exactly what the measurement is being done on the hardware platform. It's just that the hardware platform itself is not public. Yeah, the integration is not public because that's Qrypt IP. But the basic, the foundation of the quantum noise, or the foundation of the entropy, is all up for is all public.
Do you have any like moonshot projects at first that you're like allowed to talk about?
New.
Which moonshot projects like totally
Not really. We were actually last year, one of our projects was to have some sort of a photonic device. I mean, it's still out of the realm of possibilities right now, but so typically most of our hardware consists of some sort of an optical source and some sort of a detector. And we play with different sources, different detectors in certain geometries, and try to probe either some sort of a photon statistic or some sort of a quantum phenomena at the end. And we were trying to integrate these, I mean, they are still very much in research and development, but these photonic PCBs, like you have waveguides and everything built in within the PCB so that you don't have to put additional optical package within your hardware platform. But it's still sort of way out there in terms of feasibility and scalability, which for a private company is thing.
So how much your interactions with those national labs and the hardware, the engineers in the company, how much of that traveling you have to do versus?
Most of my work is local, so I didn't have to travel much. I usually go to New York often, but that's about it. Los Alamos is in New Mexico, so it's way out there. Yeah, like most of our conversations with the national lab occurs over Microsoft Teams. But we do collaborate a lot in terms of like equipment exchange. Like they'll send us a bunch of equipments that we'd need in our lab to test things out, or we'd send them our hardware platforms and they test that out in their labs, or stuff like that. Yeah. So as an intern, my first ever project was again very similar in its application. It was a hardware platform that generated some sort of a quantum entropy. One thing that luckily happened to me back then is, so during my tenure as a PhD student in Dr. Vora's lab, we used to do a lot of spatial mapping of samples, which is you basically put your sample in some sort of a cryostat and you move an entire optical setup in an XY, I mean, in an area pretty much, and spatially map what's going on in that region. And you sort of create these hyperspectral or thermal maps, you call. And so that's something that I did regularly at Dr. Vora's lab. And that's one of the projects that I worked on. My first project that I was interning at Qrypt was on an array of photodiodes. So it's pretty much an array of sorts. You don't spatially map it, but it gives you a spatial map of sorts. So I was actually lucky in a way to have a project where I felt like I could actually stand out, because the engineers there had never actually worked with hyperspectral imaging or spatially mapping something. They would look at a photodiode as an electronic component rather than an optical component, or something like a tool that gives you a map like that. And that was, and you could actually literally see the PCB design. So you could see how the connections were made on one of the planes of the PCB by mapping that array, which is again getting into too much physics. But so that's some Qrypt is actually good for that. Like they won't let you do busy work, even if you're hired new. They'll give you a project that actually really matters and let you work on that. So that's how I was able to make an impact. If they gave me busy work, or if they expected that I'd understand all of the hardware or the electrical engineering side of things, they wouldn't consider me for a full-time position. So that actually helped there. It's a tiny lab. It's mostly all electronic equipments. Like in the first year that I was there, I had to have them buy a small optical breadboard. I had to have them buy because they are all engineers. They've never looked at an optical source as something that you need to like look at. Like I've been trained to look at optics in a way that it's really sensitive, and you come. It used to happen in Dr. Vora's lab too. Like you'd set everything up, come back the next day, and nothing works because it's so sensitive. So all of our that's like that's.
It never happens in my lab.
And that's true there as well. And so it was a gradual workaround where they sort of realized, I guess in about 6-7 months, that there needs to be some amount of optical research done before it was all handed out to national labs. Before they didn't really bother much with the optics side of things because the national lab was taking care of that. But having an in-house physicist, like you have your own representative, you have your own employee doing the same thing that a national lab does. So that worked out fine. Yeah.
What is the definition of quantum entropy versus non-quantum entropy? I mean, isn't all true random generators, aren't they all based on some physical phenomenon which could be explained somehow with quantum physics?
Well, as long as they can be explained by quantum physics, they are all true random number generators. But then there are also pseudo random number generators that are based around some sort of a classical experiment or a classical algorithm that are not really, true in nature. And the entropy that comes out of those is not, I wouldn't call that a quantum entropy. But then, so it depends on what measurement your entropy comes out of from.
I mean, are there non-quantum
Yeah.
generators?
Yeah. There are non-quantum true, no. There are non-quantum pseudo-random number generators.
No, I know that's the whole.
Yeah.
So, why is it?
Yeah, because inherently a quantum, like your entropy has to be by physical laws. It's good if your keys are completely unpredictable. And for keys to be completely unpredictable, it's good that the source of those keys also comes from some sort of a probabilistic event rather than a deterministic experiment. And quantum mechanics, by its principle, is probabilistic in nature. So any experiment that you would run in the realm of quantum physics gives you an output that's entirely probabilistic. And if you convert that output with, again, like the story doesn't end there. It's a device, it's a hardware device. So it's going to add a bunch of deterministic noise. It's a field of electronic components on board. So it's very imperative that you make a device that doesn't add noise to whatever entropy that's generated from the phenomena you are measuring on board. But again, having come from some sort of a probabilistic event, the entropy that comes from that event is also completely probabilistic. And hence the keys that you trace out from that are probabilistic in nature.
So it's like every single time you talk about that,
Yeah.
always go get it.
Yeah.
As opposed to random numbers. But it was seen.
No, yeah, no, you get completely different output every time.
So this does not completely eliminate the need.
No, I mean, in some applications, pseudo-random generators are fine. It's just that if you want to build a network, or if you want to build a data communication platform that securely that's non-hackable in some sense. So if your pseudo-random number generators run some experiment that spits out a key, but that key in, say, if you collect gigabytes or terabytes of that key and feed it to a quantum computer, that quantum computer, just based on the magnitude of that data, can figure out what algorithm generated those keys. That's typically the definition of like pseudo-random, because like there's some algorithm, either classical or computational, that generates those keys. If that's hackable, then eventually with the computer we'll have in next 20, 30 years, 40 years, all of those data communication platforms are going to be obsolete. So ultimately you'd want something that's unpredictable completely, no matter what seed you put in or don't put in.